Schrodinger equation. The Schrodinger wave equation is also known as Schrodinger equation. Schrodinger wave equation plays a role of basic fundamentals in quantum mechanics. Schrodinger equation is a wave equation in terms of the wavefunction which predicts the future behavior of the electron. It gives the probability equation to determine the position and energy of the electron at a particular instant of time and space. This equation also determines the wave nature of electrons influenced by the external factors. It is a partial differential equation which uses the concept of law of conservation of energy to obtain information about the behavior of an electron. The law of conservation of energy says that energy can neither be created nor be destroyed, only it can be transformed from one form to another. It means the total energy of the system remains constant. Mathematically, total energy equals kinetic energy plus potential energy. The Schrodinger equation gives the values of wavefunction psi and square of wave function, and with these values we can get the quantum number, shape, orientation of the orbital and characteristics of the electron in an atom or molecule. It gives the exact solutions only for hydrogenic atoms, one electron system. Like nuclei with one atom only. Schrodinger equations do not provide analytical solutions for ions and molecules. The mathematical representation of Schrodinger equations is. We know that the Schrodinger equation uses the concept of observation of energy, that is, total energy equals kinetic energy plus potential energy, or E equals Ke plus Pe1. We know that kinetic energy Ke equals 1/2 mv2. Potential energy Pe equals U equals mgh. Now substituting these values in equation 1. Multiplying the equation 2 by wavefunction psi. Schrodinger gave two equations for different two condition, and they are time-dependent Schrodinger wave equation, time-independent Schrodinger wave equation. Let us discuss these equation. Time-independent equation. The time-independent Schrodinger equation, as per the name, implies that the electron is independent of time. It considers the electron to be as a standing wave or stationary wave. Overall, the electron's quantum state remains unchanged in this condition. The time-independent Schrodinger wave equation gives the analytical solution of the square of wave function, which is used to determine the electron densities like size, shape of molecular and atomic orbital, etc. The time-independent Schrödinger's equation is derived as Schrödinger gave the equation to obtain the analytical solution of the waveform. And the expression of equation was multiplying and dividing the RHS of the equation A by M, we get. Since we know that P equals mv, momentum equals mass, velocity, thus substituting this value where E equals total energy of the system, waveform or energy operator. P equals momentum of the system, momentum operator. U equals potential energy of the system. We have derived the values of both energy and momentum operator in our previous video, and the value obtained for energy operator E equals momentum operator P equals. Here we can see that the energy operator is time dependent and momentum operator is time independent. So in Schrödinger's time-independent equation we have to substitute the value of the time-independent operator. That is, on substituting the value of momentum operator we get Or, on changing the side of the RHS to LHS of equation we get plot the graph of wave function for equation D. It goes something like this. Equation D is the final expression for Schrödinger's time-independent equation,